This meeting is being recorded. This meeting is being recorded.
Uh-oh, behave, everyone.
Where's Pat?
He's there.
She's already, and he can just go if he's ready.
Yeah, Sven, we've already introduced you to the audience, so you can just start your presentation.
And you've seen my face a few times already, so.
And we can still see you on our screen along with the slides that
you
you're
do?
showing.
Okay,
Yeah.
I'm gonna,
Is his volume up?
Yeah.
We're having volume problems. Do you have your volume turned as high as it goes?
well, I mean, I'm talking in my computer.
Yeah, same
so
here.
There's nothing I can do with that.
All right.
I tried with my headset, but it was giving me issues. I can try plugging it in again. Let's see. I don't know if it might get mad at me.
Oh. Can you hear me?
Is that better?
Is that better? With the headset, is it better? That's as good as it's going to get, I think.
That's as good as we can get it.
It's not going through the system.
No.
That's what
No.
Abby said.
I'm going through my headset now.
Can you hear him at all?
Hello, hello. How are we doing?
Everybody be quiet and let us know if you can hear him.
Hello. How are
Go
we
ahead.
doing on this Thursday afternoon, April the 17th? Can we hear me okay? I don't know.
Just keep talking, Sven. It's not as loud as we'd like to have it here, but it's the best we can do.
All right. Just stop me if it's really an issue. I'll try to talk loud. And maybe I can get the microphone really close to my mouth. I don't know. So yeah, I want to talk about climate change today. It's the issue of our time, really. Of course, we've got some storms rolling in too, but there's nothing severe in the metro area right now. Nearest severe thunderstorm is Mankato, in case you're wondering. But we can maybe talk about that here as well when I'm done. I want to leave some time for questions.
Warning was Apple Valley.
Okay.
What was that? Everything okay?
Everything's okay. Keep going.
All right. Okay. So I want to talk about my climate story. I grew up skiing. My dad was in the Olympics for ski jumping. And so we were obsessed with winter snowfall. And in retrospect, what got me interested in weather was really sort of the beginning of the first noticeable signs of climate change, because we started to get those winters in the early to mid 90s where the snowfall and cold was inconsistent, and now that's become the new norm. And that got me interested in, well, how do you forecast snowstorms, and why do storms miss us, and why are some weathermen bad and some are better? And yeah, that just sort of snowballed, no pun intended, into my love of weather and climate. I also like to travel a lot, and one of the things I've noticed traveling the world is that there is a climate story every single place that I've been. You can talk to people and they know that their weather patterns are changing from what they remembered from decades ago, and it's affecting species other than humans too. I was just recently in Antarctica in January, 7th continent for me, and fascinating place that is really sort of our planet's time capsule. A lot of how we decipher our past climate beyond the temperature record depends on the ice core samples that we get out of Antarctica. It's a very harsh place. That's the reason we haven't really developed it. It's the one place on Earth we haven't taken over and ruined yet. Winter average temperatures are 60 below zero in the interior. That's the average. It can get colder, as cold as 129 below zero at the Vostok Station in 1983. And 90% of Antarctica is covered in ice all the time. It's the highest continent in terms of elevation because it's got ice cover that's 8,000 feet thick on top of a mountainous climate. I don't know if this video will play. I'm not even going to try because it might just, unless you, do you have speakers hooked up to the system?
Yes.
Well, let's see. I'll try playing it and let me know if you don't hear anything.
It's not working, Sven.
Okay, we will just ignore that then. I had some video clips in here of, so when I was there in the middle of January was the morning that it was 19 below zero in the Twin Cities, and where I was in Antarctica was 36 degrees above zero. But it was summer there, and we're on the Western Peninsula, which is quite a bit warmer. You've got tons of big icebergs there. The only other place that resembles that is Greenland, where you've got an ice sheet. That's the only place in the Northern Hemisphere where we have a huge ice sheet that breaks off into the ocean, like all of Antarctica does. But you just have these incredible colors. I'll play this. The audio doesn't matter, just to see the video of just these intense blues and whites. You think in Minnesota that you've seen all forms of white or blue until you get to Antarctica. And that color of the ice tells us how old that ice is. Because here you have ice that's so old that it's literally been compressed over time so that the air bubbles inside of it are gone. So fresh snow is white appearance to us because it has a lot of air in it, up to 90% air with ice crystals in it. And then as you compress that snow more and more through more snow piling on top of it and the glaciers just continuing to grow, that color turns bluer and greener and then eventually turns clear. And when you see clear ice that's broken off of a glacier in Antarctica, that's ice that's thousands of years old in order to get to that point. And so we would try to scoop that up from our Zodiac and use it in our drinks at dinner that night. So it was pretty cool. There it is. I was there on my birthday this year, and I'm holding up that piece of clear ice that has almost no air bubbles in it. So pretty incredible. And it's for that reason that Antarctica has the oldest ice on the planet. And just recently in January, just before I was there, scientists drilled the longest ice core yet, down 2 miles through the ice sheet in Antarctica to reach ice that was 1.2 million years old. So incredible. You don't have ice that old in Greenland or Svalbard or other parts of the Arctic. And so these are just other ways that we can decipher climate over time. We use obviously temperature records, but there's a lot of other things to determine these, what we call proxy estimations of climate. Tree rings tell us a lot about the climate. Glacier positions, lake sediments. We can go to the bottom of certain lakes and dig through the sediments, and it gives us layers, almost like a tree ring in time. And then ice cores and ocean sediments can give us, fill us in that picture. So when you see charts like this that show Earth's climate over hundreds of thousands of years, obviously nobody was taking temperature records with thermometer. We've used all those different forms of proxy data that all generally agree to give us those ups and downs in Earth's climate. And then this is specifically showing carbon dioxide, because just like air bubbles, carbon dioxide gets trapped in the ice too. And that gives us that little time capsule, that frozen moment in time when that layer of snow fell, that air in the atmosphere of Earth was trapped under that snow for thousands of years until we dig it up again and can tell what the consistency of carbon dioxide and other gases in the atmosphere was at that moment in time. Of course, in the temperature records, it's just been up and away as far as temperatures go. So we know that Earth is warming not just from the proxy data historically, but our temperature records across the globe. And when we look at the top 10 warmest years, all but one are since the year 2000. And the one that isn't is 1998 globally. So some pretty obvious trends there. And it's not that the climate's changing. Earth's climate has always changed and will continue to change, but it's the pace of change that is unprecedented for at least 24,000 years, if not hundreds of thousands of years. And the time scale of evolution for species like the polar bear is thousands of years it takes to adapt to a changing climate, not decades. like the pace of change that we're seeing now on our planet. And just this is showing another way that we can measure that the ratio of record highs to record lows. We obviously are outpacing record highs to record lows in the United States, but this is the US specifically. The other little blip there to the left is the 1930s, which was a high consistency of record highs. But we'll show you in a little bit here that heat of the 1930s was regional rather than global, like we're seeing now. And we know it's warming the world. You'll hear from skeptics who say, "Oh, how do we know it's us?" Well, we've got some pretty sophisticated modeling, and all of our measurements on the planet, we can separate out, okay, what are the different things that impact Earth's atmosphere and global temperatures? And when we take out the additional carbon dioxide and other influences, we can kind of take out the background natural climate, and it would be almost flatlined here over the last 175 years. But when we add in human causes and natural causes, it lines up with the reality of what we're seeing. So we can tinker with carbon dioxide, water vapor, solar energy, all sorts of things in these models. And the only thing that comes up with the same result as what we've been seeing over the last century is the increase in carbon dioxide, which we know that we are contributing to the most here. Last year was the warmest year on record. We showed you that top 10 list. 2024 was the hottest. Now, it's a combination of climate change. Just we're going to see more and more of these hottest years. But of course, it was a strong El Nino year. And El Nino brings warm ocean water from the depths to the surface, and that impacts global average temperature, because when we're talking about average temperature globally, we're talking about surface temperatures. And I mentioned 1936 because that's something people say to me, "Oh, what was going on in the 1930s?" Well, for one, now there have been some good studies and computer modeling done that shows that it actually was some of the first impacts of human-caused climate change in a complicated matter. We were doing farm practices that weren't working on the plains, so we were creating literally deserts in the plains by using the soil incorrectly. You know, we had East Coast farmers coming to the plains and doing farming practices that worked in wetter climates, so that when these natural cycles of droughts occurred, we literally created a desert in the plains. And when you create dry conditions over a large area of the plains, that impacts continental temperatures. And just to show you that in comparison, to the left is 1936. The only place that was hot on the planet was the United States, and then Eastern Europe and Russia. The rest of the planet was generally cooler compared to our modern averages. And then on the right, well, the last few years have not had temperatures for Minnesota that rival the 1930s. We're talking about global average temperatures, and you can see that warmth, that above normal warmth, is a global phenomenon compared to regional phenomenon from 90 years ago. And then so far this year, we're kind of off and running where 2024 left off. January 2025 was the hottest on record. And then they're still crunching the numbers for the most recent months. But one of the things that really impacts the climate of each hemisphere, as far as naturally cooling it off or not, is ice. And sea ice forms every winter in both the Antarctic and the Arctic. And this year, again, Arctic or Antarctic sea ice was below normal, and Arctic sea ice. And the reason we kind of obsess over how much sea ice there is or isn't is it's really the food web of the Antarctic and Arctic ecosystems. Not only does it keep the Arctic and Antarctic cool, but it's also important for the whole food web, because as that sea ice melts slowly in the long Antarctic or Arctic spring and summer, algae forms in the bottom of that sea ice where there isn't otherwise. In Antarctica, there's very little exposed soil. So this is kind of the soil of the Antarctic Ocean, is sea ice, that algae growing underneath, and that feeds bacteria and phytoplankton and zooplankton, and that feeds the krill and the fishes and squids, and that feeds the whales and seals. So when we have less sea ice, you have translates literally to less food potential as well for the Antarctic oceans. And then I've got a little Jane Goodall there on the right, to demonstrate that, you know, we are connected to everything on the planet. We like to think of ourselves as separate and superior, but you look at just a basic food web ecosystem and everything is connected. You can't tinker with one and not mess up the other. And that includes us too. We might be at the top of the food chain, but we're still part of the chain. Antarctica this year had some pretty low sea ice again after 2 record years of Antarctic sea ice. This is just plotting from last year into the beginning of this year so far. The blue line is this 2025 winter season, and then compared to the average 30-year average, which is the gray line above it. We were almost average for a period of late December to early January, and then dropped back to below average sea ice cover. And one of the startling things about Antarctica in the last several years is, well, the Arctic has been steadily warming rapidly, just indisputably over in the most recent decades. Antarctica has actually been kind of flatlined because it's a whole continent covered in ice at the South Pole. It's more resistant to the changes that a greenhouse effect has. But we know that eventually the warming oceans, as well as the warming atmosphere, will finally take a toll on Antarctica. And the big question now, the last couple of years, is that have we jumped off that cliff? Because this is plotting all the years of Antarctic sea ice. And you can see they're mostly in that gray range, up and down some, but within a certain range. And then 2023 and 2024 are the blue and red lines that are way below that. We saw the last 2 years were off the charts low for sea ice. And if anybody understands statistics, 2023 was 3 standard deviations below the average, which is off the charts, literally almost improbably low sea ice. So the question is, have we reached some new normal, or again gone off kind of a cliff in Antarctica? It's too soon to know, 1 or 2 years, but we know that eventually these impacts would happen. And when we increase the average, going back to statistics, this shows the bell curve. You increase the average, you exponentially increase the extremes, or decrease the extremes on the cold end. So when we talk about, warming things 1 or 2 or 3 degrees, it doesn't sound like a lot, but when you're warm the average that much, you're really increasing those extremes on either end exponentially more, just because it's a matter of probability or area under that curve. To give you an example of how this works statistically, back in February, this was back in February, the average high temperature for the date is 34 degrees. A standard deviation for that date for high temperature in the Twin Cities is 11 degrees. So that means you would expect the normal range, 2/3 of the data should be anywhere between 11 degrees less than 34, so 23 degrees, to as much as 45 degrees. And that makes sense to us. It should be in the 20s, 30s, or 40s around February 20th. But to give you an example of just how crazy off the charts 3 standard deviations is from normal, that would be a high of 67 degrees on that date. And we've never been warmer than 65 degrees. So that's how improbable, how extreme a figure that is 3 standard deviations from the average. And so that's the extreme that Antarctica saw 2 years ago in sea ice. Arctic in the northern hemisphere, this is the area that affects us the most, directly impacts us and the northern hemisphere. 2024 was the second warmest on record. So remember, 2024 was globally the warmest year, but in the Arctic specifically, it was just their number 2. But pretty much each year has been breaking records. So they got a little bit of a break last year with only the number 2 warmest spot. And so I mentioned that we've been seeing this steady change in the Arctic. This is plotting average sea ice extent or sea ice cover in the Arctic in the red line. And you can see there are ups and downs, of course, each year, just the variations in weather, but an obvious downward trend from 1979, which is when our satellite records for sea ice start. But Antarctica up through 2015 actually saw sea ice slowly increase. And then 2016, 2017, we saw this huge, again, off the cliff drop in sea ice. And so everybody's wondering, is this now finally that downward trend in ice that we've been seeing in the Arctic already reaching the Antarctic? And then we had a couple years where it went up a little bit. You can see 2020, 2021, but then you get to 2023 and 2024, and we outdid any previous records. So it's very dynamic, Antarctic sea ice, because it is a continent literally situated in the middle. Ocean currents, wind patterns, a lot of things go into sea ice formation there other than just temperature as compared to the Arctic. And we call this rapid warming in the Arctic, which is greater than the average on the planet, this feedback warming. So while the global average temperature you can see in blue since 1960 has been a steady increase, the Arctic after about 1990 just really takes off and separates. And so we're seeing this accelerated warming in the Arctic compared to the global average. And the reasons for that are how different the Arctic and the Antarctic are. We tend to think here at mid latitudes far away from these places that they're just both cold, icy, snowy, inhospitable places, but they're actually very different. They are cold, snowy, and icy, but they are very different. Antarctica, as I mentioned, is a continent bigger than Australia that is situated at the South Pole, which still gets dark for half the year at the poles. No matter what we do to the climate, you still have the solar cycle through the year. But the Arctic is mostly ocean, surrounded by continental land. And so that's why these two places are behaving differently in our warming world. And the Arctic is warming so much quicker because the oceans are warming so much more quickly. And the Arctic is mostly ocean. You have ice on top of ocean, but it's mostly waterfront in the Arctic. And global ocean temperatures have been reaching record levels. These are plotting ocean temperatures back to the early 80s. And 2020, 2023, 2024 all have been new record temperatures for the oceans. And we know that we realize how much the planet has warmed over the last 50 years. 90% of the warming so far, 90% of that heat is being absorbed by the oceans. And you can store a lot more heat in water than you can in air. And that's consistent heat that's kind of trapped there. And in the Arctic this year, we actually set a new record. So we measure in particular the maximum of sea ice. So at the end of the Arctic winter, which happens sometime in March, what is the maximum ice coverage? And then we measure the minimum at the end of summer, which is usually sometime in September, to kind of give us a baseline comparison year to year. And this year narrowly broke the record for the #1 year for the lowest amount of sea ice since we've started keeping satellite records in the 1970s. And while it doesn't sound like much, 14.3 million square kilometers compared to the 1981 to 2010 average of 15.6 million square kilometers. That's difference of 1.3 million square kilometers is the size of 2 states of Texas. So basically we had 2 states of Texas less of sea ice in the Arctic. And that's has a big impact on the climate. So this is what it looked like on March 22nd, which is when they declared the maximum extent this winter. And in white is where we had sea ice. And the orange line, which might be hard to see, but it's a faint line, that is where the average extent of the ice should be based on the 1981 to 2010 average. And you can see pretty much everywhere around the Arctic doesn't quite reach that orange line. And so collectively that adds up to those 1.3 million square kilometers of less sea ice. The blue line is this winter season. Orange is 2022, 2023. And you can see we came in, if you look to the right there in March, we were just under the 2023 ice record to set the #1 record. And then this is just comparing January 2025 to January 1980 as an example of the difference in ice. So the bluish gray color is where we have ice cover this year and in 1980. But in white on the edges there, you can see where we had ice cover in January 1980 that we don't have anymore now. And that's a lot of ice there over that 45-year period that we don't have anymore. And this is the ranking, the top 9 seasons for the lowest Arctic sea ice. And the one thing you'll notice if you're looking at all the years, they are all since 2006. So of those 50 years of satellite records, all of the top 9 are just since 2006, which just shows this obvious trend and what's happening with ice. And again, ice and ocean temperatures tell us almost a better picture of the big picture, what's happening with our global temperatures, because temperatures can vary, air temperatures, of course, up and down, but your pool or lake cools off and heats up more slowly, and the same thing with ice. And so measuring those give us a really good idea of the bigger, longer term projection. And so this feedback, this Arctic acceleration and warming is driven by this less sea ice. So when you have ice covered water, it's reflecting up to 90% of the sunlight back to space. So think of, we know here full well in Minnesota that after a fresh snow, it can be sunny, but temperature won't warm up much because all that sunlight is being reflected back and blinding your eyes if you're trying to drive. But open water absorbs up to 94% of the incoming sunlight. We don't think of water that way, but when you look at Google Maps, you look at the continents and the ocean is a dark blue color. It's a dark surface. So it's like a parking lot absorbing sunlight versus sea ice or snow cover, which is reflecting it back. So not only are we warming the atmosphere of the Arctic, just like the planet, which is warming the temperatures, but by doing that, we're creating less ice, which only feeds back into the loop and accelerates that warming even more. And so that's why the Arctic is really seeing, and the Antarctic are seeing temperatures just really take off. But in particular, the Arctic, because as we mentioned, it's so influenced by ocean temperatures, which are at record levels. And it's not just that we have less sea ice, we have less old ice, which tells us that we're eating into our deposit of older ice. So one of the things we measure is not just the ice cover every year, but the age of the ice. And back in the 80s, at the end of the Arctic summer, so when you had the minimum of sea ice, about half of what was left in September was ice that was 5 years or older. So that means that because of the long Arctic summer, but not warm enough to melt all the ice, of course, because it's cooler than our summers, you still had ice left over, ice that hadn't melted even for several years in a row. But now in the 2020s, the ice that's left is about 8% of it is multi-year ice only. And so that tells us that we're really eating into that ice. And that's why we're talking about potentially within a few decades, we could have an ice-free Arctic at the end of the summer. And the reason that's alarming is, you don't have to be a astrophysicist to know that if you have 2 jars of water at the same temperature and you have one and you put some ice in it and the other you just leave water and you put it in the freezer, which one's going to freeze quicker? The one that has some ice in it, right? So when we have less sea ice or no sea ice left in the cup going into fall and winter in the Arctic, it's just going to take much longer even to cool off the water to form sea ice. And so you're just decreasing that season of ice, and it's just this effect all runs away. And so maybe you're thinking, well, what the heck's he talking about the Arctic and Antarctic so much? We're in Minnesota. Well, it has a huge impact on our climate because we kind of joke that this, in the dead of January, welcome to the Arctic. Well, Arctic heavily influences our climate. These are showing wind roses. So magnitude and direction of wind on average over a 30-year period. So on the left is January, the right is July. And so what you're looking at is the magnitude. You can see out of the Northwest, that biggest color bow there shows that the dominant wind in January is a northwest direction, which is coming from the Arctic. And in July, it's more mixed out of the south, sometimes out of the northwest, but largely dominated by a southerly direction. So in the summer, the Arctic has less influence on our climate, and that's why our summer temperatures are warming more slowly over time than our winter temperatures, because the Arctic is warming 2 to 4 times faster than the rest of the planet, our winters are also warming at about double the pace of the rest of the planet's average or the rest of our year because of that Arctic influence. And so this is just showing on a statewide basis that those temperature trends, about a degree per decade in winter compared to just a quarter of a degree per decade in the summer. So our winter warming is about 3 to 4 times more than what we're seeing in the summer months. But interestingly, well, summer, particularly July and August, our warmest months of the year, are almost flat compared to 50 or 100 years ago. The beginning and end of summer, June and September, are some of our fastest warming months in the warm season. So, which tells us summers are getting longer. They're not necessarily getting more intensely hot yet, but they are getting longer. And of course, that affects growing season, and which is great if you're a gardener, but not good if we want to keep away mosquitoes and things that carry diseases or invasive species. There's also unintended impacts of warming the Arctic so rapidly. It's changing jet stream patterns, which we saw actually a really good example of this twice this winter, where we had those two, well, we can call them extreme cold outbreaks for this time of year. I was talking at a university class a couple weeks ago, and they were all like 20, 22 years old. And I felt like an old man telling them, well, you guys don't even remember what real winters were like, right? Because they didn't know the 1990s or 80s or anything before that, literally. And this winter, 19 below zero seemed probably extreme to them because they've never experienced 30 below zero. The last time we hit 30 below zero in the Twin Cities was 1996. And that was a number that we used to hit every few years a century ago. It wasn't every winter, but every 3 or 4 years on average, we would reach 30 below zero in a winter. And now we haven't done it for almost 3 decades. And will we ever do it again? Hard to say. Depends on a lot of things, but it's those frequencies of cold that we used to have, which are much less and more frequent warm periods. But when we're warming the Arctic so fast, we're decreasing the temperature contrast across the hemisphere, which drives the jet stream. So you can imagine the planet is warming, of course, but if the Arctic is warming at 2 to 4 times the pace, that decreases the temperature difference between mid-latitudes and the equator and the Arctic. And that's what drives the jet stream, because as air wants to move from where it's colder to warmer, that's what creates the wind that creates the jet stream. Then the Earth tilts that wind to move generally west to east. But when you decrease that contrast, you decrease that wind. And so slower jet streams become more wobbly, and this allows these bizarre intrusions of warmer cold air. And this is just a good visual of that. So when we talk about a polar vortex, when it's stable, that's actually a good thing. A strong polar vortex means that cold air is generally contained to the north, but when it's weaker, with weaker jet stream patterns, you get cold air that shouldn't be as far south as it is. So in February in particular, that mid-February cold snap was legitimately cold for mid-February. That's what was unusual about it, to see that kind of cold that late in the winter. In January, it wouldn't have made any headlines, but mid to late February, that was pretty cold. And that was because of this setup where we had record warmth deep into the Arctic. This is what precluded that outbreak. So that you can see on the left, in mid-February, the Arctic air mass was split in two because we had this extreme heat in the Pacific moving up to Alaska, up to literally the North Pole. They had temperatures that were 40 degrees above normal in Arctic Alaska and above freezing almost to the North Pole, splitting that Arctic air into two and literally pushing a chunk of air south towards us that then we had spinning around us for a week or so there in mid-February. Whereas on the right, this is a more normal looking pattern where you have the blob of cold generally centered around the North Pole. Of course, it's got fingers and arms, but not split into two or even weirder shapes that we're seeing more and more because of this extra heat in the oceans and other parts of the continent that are just completely altering weather patterns and jet streams. And so this is showing both that mid-January and mid-February cold snap. The February one in particular stands out on the right. And so that while we were having temperatures that were almost 20 degrees below average, averaged out for that week in mid-February, notice up in the Arctic, Hudson Bay and Greenland, temperatures were 20 degrees above normal there. So literally we had the air that should have been in the Arctic, and the Arctic had the air that should have been over mid latitudes, and this bizarre flip-flop. So it's one of these sort of unintended consequences of climate change that we're seeing in the middle of continents, both Minnesota, but also parts of Asia and Siberia are seeing this too, where we're getting, it's not just every winter's warmer and warmer, we are seeing an increase in these bizarre outbreaks of unusual cold because of that complete alteration of the weather patterns with the jet streams. And this is showing what kind of led up to that January cold outbreak. Record warmth in Alaska, all of the Arctic in Canada. And we know that that warmth was made 2 to 5 times more likely due to climate change. So remember, I showed you the bell curve here. The way we can decipher this is we say, okay, this temperature was 20 degrees above normal, and that's, this many standard deviations from normal. And we know that we've warmed the average temperature in that area 3 or 4 degrees or whatever the case may be. And so we can statistically extract what the probabilistic difference is. So when you hear about these rapid attribution studies that we're able to do now, some of it is more sophisticated, like in a hurricane. How can we extract what was the climate change impact on that hurricane compared to what it would have been otherwise? There's some sophisticated modeling that goes into that. But when we're talking about like day-to-day temperatures, we can just do a statistical analysis like that based on the data set that we have for a particular area. And then of course we had that cold snap in January, where it was 19 below zero, and I sadly missed it in Antarctica. But it just sounds weird to say, but then a week or two later, we had record warmth at the end of January. So this is January 30th, 51 degrees. So to go back to this setup, in one spot, we're in that cold intrusion. And then a week later, we move into the extreme warm intrusion. So we are seeing more of this back and forth between extremes than we used to historically. And we can measure that with standard deviation and variance. And then this is, so this is that date, that 51 degree record high in January, showing, again, doing the statistical analysis. This is from Climate Central. They do these rapid attribution analyses for temperatures. And that record high of 51 we had on January 30th, we can statistically say was made 4 times more likely due to climate change. So of course we have ups and downs. It's not that it never hits 50 in January, but we can say that day in particular, it was made more likely because of climate change. So you already had a weather pattern that would have led to a warmer day, but because of the warming of the average temperature, it made it more probable that we reached that particular temperature that day. This is from Dr. Mark Seeley showing heat waves, some of our historical heat waves. And of course, the 1930s get a lot of attention, but we're seeing more and more heat waves now that are dew point influenced. So undisputably, we had our hottest temperatures in the state of Minnesota in the 1930s. And hopefully we don't get to those readings again for a long time. But now we're seeing higher dew points. It was we talk about a dry heat, right? In the summer, the 30s were a dry heat. So the heat index was actually lower than some of our more modern heat waves where the temperatures were cooler. But now we'll get a 98 degree day, but with an 81 degree dew point, which used to never happen before the 1990s. So we're seeing more and more of these higher dew points. You warm up the atmosphere, it can hold more water, and that increase in water vapor is creating these extreme precipitation events that we're seeing too. So these 3, 4, 5 inch rainfalls that used to happen much more rarely are happening more and more. And of course, this has impacts on our biodiversity and animals on the planet. Most scientists agree we're in a 6th mass extinction event. They've determined there are 6 of them in history, and this is the first one caused by another species, us. The combination of changing the climate, of course, but also destroying habitat for a lot of animals. And so the blue line is the rate of extinctions, and then the red line is human population. And sadly, they kind of go hand in hand. And that's similar when we plot human population and carbon dioxide emissions. You can see as there's more people, not surprisingly, we're producing more greenhouse gas emissions. I taught earth science class to middle schoolers in the pandemic, and when I show this graph back here, one of the kids said, well, we just need to kill more people and then we'll solve the climate change. You know, the very simple logic of a 14-year-old, right? I'm like, well, maybe let's not do that. Although, boy, some people in the world sure seem to be trying with wars and stuff. But we just got to live sustainably. We know how to do that. And we've got an incredible brain that can help us do that too. But a lot of times people say, well, what about China? And China is a big polluter, but the U.S. It pollutes more greenhouse gas emissions per capita. So on a person by person basis, we produce more than somebody in China, and certainly more than in India. But because they have more people, they produce as much or more greenhouse gas emissions. And again, just to remind you, it's not that things are changing; it's that pace of change, and that affects things like polar bears that I talked about at the beginning. I've led a few groups up to Churchill to see polar bears, and that Western Hudson Bay polar bear population has seen a 27% drop in the population in just a 5-year period. So they do a census every 5 years because I guess it's hard to count polar bears. I imagine mostly by helicopter. And the 2016 to 2021 survey found a 27% drop. And that's largely driven by fewer cubs surviving. Because a female polar bear has to put on a lot of weight in order to have a successful pregnancy for complicated reasons that polar bear biology, but it's they're kind of, I think, moms of the year in the animal kingdom for what they go through for their cubs. And so Hudson Bay, seeing the same thing, that Arctic sea ice that I was showing you those charts, Hudson Bay is included in that. And so Hudson Bay is an example of sea ice that's seasonal. So the sea ice goes out completely in the summer of Hudson Bay, but then it completely fills in for the winter, kind of like a big Minnesota lake. But sea ice used to go out in Hudson Bay sometime in July, and now it's happening more and more in June. And sea ice used to form early to mid-November again, and now it's happening more and more into December. So that shrinking window of sea ice on Hudson Bay means less time for polar bears to eat because they need sea ice. That's their hunting platform to eat seals. That's their primary food source. They need that high fat diet. So when there's no sea ice, they really aren't eating. I mean, you'll see video of polar bear chewing on blueberries once in a while, and people are like, oh, isn't that cute? Well, it does calorically does nothing for an animal that size. They can't live on that. Or if they happen to catch a bird or something, they need that super high fat, super high calorie diet from seals, and they can adapt. Polar bears are related to grizzly bears. They can actually produce offspring. A polar bear is a tundra grizzly, essentially, that evolved since in the last ice ages to hunt seals on sea ice. So animals can evolve to changing climates, but again, it's over the course of thousands of years, not 50 years. And of course, it's having impacts on things like home insurance. So if people don't want to believe scientists and temperature graphs, just ask your insurance company, why are the rates all going up? They know what's going on. And there's people always ask the solutions, and we kind of know the solutions, right? We can all drive an electric car or reduce gas emissions and a list of things. But I tell people now we're in a period where we're kind of on a war on truth and science. So we need to get back into a setting where we value science and research and finding solutions rather than cutting things to that. And I always like to use this chart because we can just, again, what can we all do? And this just shows the impact of all sorts of different things on carbon emissions. And again, to go back to the population thing, having, one fewer child or something, it has a huge impact. What is it on here? 2 children is the equivalent of, or no, it's not the number of children, but having 1 fewer child all the way to the right is the equivalent of triple the equivalent of living car free, or about 5 or 6 transatlantic flights, having 1 fewer child. So then that's because, again, we're not living sustainably. So fewer humans that are producing more or using more energy, producing more greenhouse gas emissions would help the planet, or we just learn to live sustainably like we once did at one time. Of course, we don't need to go back to the Stone Age to do that either, but this shows like how other countries live compared to us, to give you the idea that it's not equal. We're not all living sustainably or unsustainably. It's certain countries and certain habits that are doing it. This is comparing if everyone lived like the people in this country, how many Earths would you need? So in India, which produces a lot of greenhouse gas emissions because it's a developing country with over 1 billion people, but on an individual basis, if everybody lived like the people in India, we'd only need 7/10 of an Earth. Whereas in the UK, you'd need 2.5 Earths. And then you go down to the bottom, second from the bottom is the United States. We would need almost 5 Earths if every person on the planet lived like an American did. And then beating us is the United Arab Emirates, because you see all those crazy skyscrapers and pools and golf courses in the desert, which look cool, but like that's the most unsustainable way to live. But on our local, our scale in the US, living in Phoenix, Arizona, not sustainable really. We need to alter what we're doing to make that a sustainable existence. And it turns out you need water, right? There's different things, there's all sorts of solutions in terms of like building materials. A big source of carbon dioxide emissions is building and construction, from the operations, the industrial part of it, transportation, different materials. And we can create, this is something that already has been happening a lot more, of course, in recent years, is building more sustainable construction, which is good for the planet, but it's also good for your energy bills. You put in better insulation, better windows, better sources of energy, and you're going to use less heat or air conditioning to heat or cool your building. But another thing that doesn't get talked about a lot is land use. The way we use our land on the planet has a huge impact on carbon emissions. So this is showing the loss of forest in the Amazon. And you can see in dark blue is where we've deforested large swaths of the Amazon in Brazil, and then showing how that's altering the climate there too on a local scale. So the Amazon is getting drier because it turns out that it's not the rain that makes a rainforest, it's the forest that makes the rain. All that evapotranspiration in a warm climate creates that moisture that then is able to be condensed out into showers and thunderstorms. So when you cut down the trees, you're literally creating areas of desert now into the Amazon. And the Amazon is one of Earth's many pairs of lungs to help take carbon dioxide out of the atmosphere. And so when we cut down forests, we're literally shooting ourselves in the foot in this situation. This is showing that over time, from left to right, as we're warming things up, we're creating drier conditions in the Amazon. Minnesota, we only have a tiny fraction of our original prairie. So in yellow is where the prairie used to be, and the orange areas are where they are now. We have about 1 or 2% left of our prairie. And so nobody's saying, we got to just get rid of every farm, but the way we use land matters. Grass, Kentucky bluegrass that everybody has in their lawns is the second from the left there, has a shallow root system, doesn't store much carbon, but prairie plants, deep roots, store carbon deep, and also can handle drought and flood cycles better than our shallow rooted plants. And corn has shallow roots. An intriguing idea that's come out in recent years is the Trillion Trees project, where they use some modeling to discover that if we look at areas that we could reforest on the planet without, moving cities or suburbs, without altering the human occupied land, if we just reforested part of the areas that we've deforested, we could take out a sixth of human carbon emissions. So that would be huge, just by planting a few trillion trees, just by putting back a fraction of what we've deforested could have a big impact on carbon emissions. So rethinking how we use the land can have a big impact. And that goes for prairies too. Restoring prairies are a huge carbon sink. Kelp in the oceans, the Antarctic Ocean absorbs a lot. I got to interview Jane Goodall several years ago, and she kind of gives her 5 reasons for hope because it can all seem very daunting. And she talks about the human brain. We can do stupid things, but we can also be very smart. And the resilience of nature. When we restore an area or just leave it alone, it'll come back a lot of times. And the indomitable human spirit, the determination of young people, and the power of social media, which can be both good and bad. And then I have some other stuff here, but I want to make sure I have some time here for questions. If anybody has any. I know it's better to be in person, and I apologize for that again, but hopefully this kind of worked.
It's scary. Questions?
They just had on PBS a thing on nature about how soil affects holding carbon in the soil, and how important like mushrooms and what a big factor that is in the connection between tree and soil. Can you speak to that a little bit?
Yeah. Did you happen to be watching the Nova on PBS last night? About forests? Yeah, and I saw that too. And how it's, and to go back to that Trillion Trees project, that's that Fred Pierce who's in that Nova. And he talks about it's not just about planting trees, period, because a lot of we're just planting trees, monoculture, one tree species in rows like we do with corn or something, and it doesn't have this impact, but it's the entire ecosystem of a forest that helps to utilize carbon. And so, yeah, when we're obsessing over tree roots, it's because the deeper the roots, the deeper into the soil, the plant will store the carbon. So yeah, soil is really vital to that and how we use it.
Other questions?
Howard? Your question. So, Seth, imagine that your slides are making use of information from large governmental organizations. Perhaps I'm wondering if the downstream that organizations will have any impact on meteorologists and climate folks to monitor what's going on.
Yeah, absolutely. Let me pull up an example of that here. So hopefully you're seeing my screen again.
Yeah.
So I'm going to show you, this is a big impact. These are our weather balloon launch sites. And like I told these college kids a couple weeks ago, I'm like, yes, we still launch weather balloons to get data. They kind of think of it as like so archaic, like why don't we use drones or something? But this still works better than most things. What did I just do? So what I want to show here is these are our weather balloon launch sites. And what we do in theory is launch twice a day. So we have one, the Weather Service office in Chanhassen launches a weather balloon at 6 a.m. at 6 p.m. And that gives us that vertical profile of the atmosphere, temperatures, winds, humidity as you go up. Otherwise, we have observations all over the surface, right? At every airport or whatever, but you need to know the three-dimensional view of the atmosphere. And the only way we can do that is with weather balloons. When you're on a commercial flight, they'll take some weather data too, but obviously it's moving and they can't cover everywhere. And then we kind of fill in the gaps with some satellite data too. But really, it's crucial to have these weather balloons. And then we have severe weather. Like if today were a potentially more intense day, they would launch another weather balloon midday at lunchtime to give us another view of the atmosphere closer to when storms could blow up, to see what's changed. Is it more unstable, less, or more stable? And so already what we're seeing, and the reason I brought up this map is you'll notice west of the Twin Cities, there's a huge gap without balloons now. This is what the map looks like now. Whereas if you go straight west from the Twin Cities, you could conceivably not reach another weather balloon launch site till Boise, Idaho. Whereas we used to have one in South Dakota and one in Wyoming and two others in Nebraska. So what I really do worry about is in severe weather season, those areas to our west where our weather comes from, we don't have a picture of what's going on aloft. Computer models will just guess. The way a computer model will work is they'll say, well, let's say we're looking at temperatures at 10,000 feet. Well, the temperature was this in Bismarck and that in Nebraska and that in Boise and that in Minneapolis. So in the middle, it must be this, and just averages them together when that's not probably the case, right? But it's a best guess. So we already have gaps in our weather balloon network, and ones that are still launching, they're reducing them to one launch a day instead of two launch a day. So we're losing data in terms of time and space. And that's just one example, because it's cutting back staffing. You require people to do this and people to monitor it and take in the data. And a lot of people younger people don't remember that we already cut the weather service in the 80s a lot too. There used to have a weather service office in St. Cloud and International Falls too. So we're already kind of on a bare bones weather service that, if anything, needed more money, more investment. And it's also something where I've read that, like the research dollars we put into health research, right? For the National Institute of Health, it's something like every dollar you put in, we get back $2. So it's a good investment, right? Well, the money we put into NOAA and the Weather Service, some estimates are we get for every dollar, $50 to $70 of investment. So cutting it makes 0 sense. In terms of whether it's severe weather, protecting life and property, think of how much money can be saved with better warning, better forecast. And so, yeah, long story short, we're putting worse data into our computer model. So forecasts could potentially get less accurate.
Did you have more, Ben?
Got one more.
Just come around from there, maybe.
See if you can hear me. Can you hear me?
I hear you.
Okay. Well, the question would be, you said that the ice in the Arctic is melting. Any predictions on when it'll be ice free and ships can pass from Greenland to Pacific Ocean?
Yeah. I mean, some estimates are as little as 10 years. I think that's probably on the soon extreme. And some of them are as late as maybe 30, 40 years, but sometime in at least my lifetime, and a little too, because once we reach that tipping point, it's going to be hard to go back. And then it's going to require things like some real innovation that maybe we'll come up with. I've seen things, there have been some crazy theories about installing white platforms in the Arctic to mimic ice, sea ice, in terms of reflecting back sunlight. I mean, we might have to get to that point at some point, but yeah, anywhere from 10 to 50 years is kind of the estimate. But what I will say is, in some of the things, when it comes to ice in both the Arctic and Antarctic, those things have been exceeding what our computer model projections have had. So coming sooner than what we thought in most cases.
Got maybe one more, or are you ready to? Want to say something? Just speak.
Okay, I think we're finished with today. Thank you, Sven, for coming. A lot of information to think about and to process. I'm glad we work. So
Thank you. Yeah, again, I'm sorry to have not been there in person. We'll have to do a redo. Put the radar up there for you just so you can see what's going on with the storms. We've got there's a warning down by Faribault, headed towards Owatonna. I think we're good on severe weather here. These showers that came in earlier, dampening the atmosphere. So
Thank you.
you're welcome. Have a lovely evening. Stay dry.
you.
Good.